Welcome to Godlike Academy. If these cloud certification lessons help, hit subscribe and like. It really helps the channel. Imagine a highway system where every car has to take the longest possible route to reach its destination, and traffic lights are completely random. That is exactly what happens to your users when network performance and routing are poorly designed. In this lesson, we will explore how to keep data moving fast and reliably by mastering latency, throughput, and intelligent traffic routing strategies. If you skip proper configuration, application response times will spike past acceptable thresholds, causing customer churn and triggering automatic scaling penalties that drain your cloud budget overnight. Here is what we will cover. We start by distinguishing between latency and throughput, the two metrics that define user experience. Next, we look at global routing strategies like GSLB and Anycast. Then we walk through a step-by-step design process for high-performance routing. Finally, we discuss protocols and edge optimization to keep your infrastructure snappy. Mastering these concepts directly impacts your ability to pass performance architecture questions on the certification exam, and neglecting them will cause unpredictable failover behavior during actual deployment windows. Let's start with the fundamentals. Latency is the time it takes for a packet to travel from source to destination, usually measured in round-trip time or RTT. Throughput is the volume of data moved in a given time period. As an infrastructure designer, your goal is to minimize latency by reducing physical distance and hops, while maximizing throughput by ensuring sufficient bandwidth and efficient protocols. Confusing these two values will lead you to over-provision expensive network interfaces when you actually need faster geographic placement, causing budget waste and degraded application responsiveness. Traffic routing is the mechanism that directs data across the most efficient paths. It ensures reliability and speed by intelligently selecting where traffic goes based on geographic proximity, server health, or load conditions. Understanding this concept is crucial for designing solutions that meet strict performance SLAs. If you misconfigure routing weights or ignore endpoint health probes, your load balancer will continuously send requests to failing instances, triggering cascading timeouts and violating the 99.9% availability targets required for production workloads. To manage these metrics effectively, we employ various routing strategies. GSLB directs users to the closest geographic data center, significantly reducing latency. Anycast routing uses a shared IP address across multiple nodes, letting BGP metrics route traffic to the nearest node. CDNs cache static assets at the edge, offloading traffic from the origin server entirely. Mixing these up during an exam scenario will cause you to select the wrong service for dynamic database queries, leading to unnecessary cross-region egress fees and degraded user experience. Now let's design a high-performance routing solution. We will follow 3 key steps. First, we define latency targets based on user expectations. Second, we select the appropriate global strategy to meet those targets. Finally, we implement health checks and optimization to ensure resilience. Skipping the initial requirement gathering phase will result in over-engineered network topologies that fail automated compliance audits and introduce unnecessary routing loops during peak traffic events. For the second step, selecting a global strategy, we can use Terraform to define a latency-based routing record. This configuration directs users in the US East 1 region to a specific endpoint. The latency routing policy block ensures that Route 53 evaluates the user location and routes traffic to the nearest healthy region automatically. Running as network DNS record, set a list without verifying TTL settings will cause stale DNS propagation. forcing clients to connect to deprovisioned endpoints during active maintenance windows. With the strategy selected, we move to the next phase. We must define our latency targets clearly and then select the global strategy that aligns with those requirements. This ensures that every routing decision supports the overall performance goals of the application. Failing to document these thresholds explicitly will lead to ambiguous SLI reporting, making it impossible to troubleshoot bottlenecks when packet loss exceeds the acceptable 5% threshold during high concurrency events. Visualizing the traffic flow helps us understand how data moves through our infrastructure. In a CDN-enabled architecture, the user request first hits an edge node. If the content is cached, it returns immediately. If not, it fetches from the origin server and caches for future requests. This flow minimizes latency for repeat users. Misconfiguring cache TT L values will cause excessive origin pull requests, overwhelming your backend compute resources and triggering automatic throttling during sudden traffic spikes. Finally, we implement health checks and optimization. This involves defining our latency targets, selecting the global strategy, and then ensuring that traffic is only routed to healthy endpoints using automated health probes. We also optimize protocols to handle packet loss gracefully. Neglecting probe interval configuration will cause delayed failover detection, leaving active connections stranded on unhealthy nodes and violating your established recovery time objectives during planned maintenance cycles. To implement weighted distribution, we can configure a load balancer using Nginx. The upstream block assigns weights to backend servers, sending more traffic to powerful instances and less to smaller ones. The proxy pass directive then routes requests to this weighted pool, ensuring efficient load distribution. Setting incorrect weight values will starve lower capacity VMs of resources while overloading primary nodes, causing uneven response times and triggering false positive health check failures across your deployment tier. Remember this key principle. Always aim to terminate connections as close to the user as possible. By utilizing edge functions, you can perform authentication or header manipulation before the request even hits your primary infrastructure, drastically reducing latency. Implementing this correctly will cut average response times below 200 milliseconds, while ignoring edge termination forces all traffic through centralized gateways, creating single points of failure that crash under moderate concurrent load. Let's check your understanding. Which metric measures the time it takes for a packet to travel from source to destination, and which strategy uses a shared IP address to route traffic to the nearest node? Think about the definitions we covered. Answering these correctly demonstrates mastery of core networking concepts, while mixing them up during the certification exam will cost you immediate points on performance architecture questions that require precise terminology matching. To recap, we explored how latency and throughput define network performance. We compared routing strategies like GSLB, Anycast, and CDNs to manage traffic efficiently. We designed a high-performance routing solution by defining targets, selecting strategies, and implementing health checks. Finally, we optimized protocols and edge caching to ensure resilience. Mastering these implementation details will directly improve your score on practical design scenarios, while overlooking probe configurations will cause cascading service failures during actual production deployments. For the AZ-305 exam, focus on distinguishing between latency and throughput metrics. Be prepared to choose the right routing strategy based on geographic distribution requirements. Remember that health checks are essential for automated failover, and always consider edge caching to reduce origin load. Practice identifying the best solution for high-performance network designs. Failing to memorize specific CLI parameters and service capabilities will result in incorrect architecture selections when evaluating complex multi-region deployment scenarios under strict time constraints. Thanks for watching. Subscribe for more cloud cert lessons, and I'll see you in the next one.